Hi, good afternoon, and thanks for attending my keynote on technical debt in practice. My name is Neil Ernst. I'm an assistant professor at the University of Victoria, studying in the Department of Computer Science. And thanks very much to the Research Software Conference for inviting me today. I do research in software engineering, and one of the issues that I look at is the issue of technical debt in software. The research angle there is to identify and understand when and why technical debt's being incurred and figure out ways in which we can repay it. From a practical angle, the unpaid technical debt in our software generates interest payments. These are increased defect counts, lower quality, and ultimately slow releases of features to the stakeholders. But one of the messages of the talk today is that technical debt's really everywhere, and that it's not always a bad thing to have technical debt in your software. The context here is that software, as you probably well know, doesn't go anywhere. We just keep adding more and more software, more code to our code bases. Here's an example from the Linux kernel showing how much new code is being added every year. Very little of this code ends up disappearing over time. The other context here is that we're in an era where we want to computation all the things. So you probably understand that in almost every research discipline that I'm aware of at the university level, there's some form of computation involved or coming along. We have computation in law, looking at legal texts. We have computation in sociology, looking at qualitative data analysis. And of course, we have quantitative disciplines like economics, like physics, that have used computation for a longer period of time. So that's the background to understanding why technical debt is relevant here. I really think software is entering or has entered what I might call the Moneyball era. So Moneyball was a book and then later a movie with Brad Pitt that looked at the application of essentially data science to the sport of baseball. The idea here is that in baseball teams, and now in all sports teams, you want to identify key attributes that emphasize, what makes it a good team. Measure your players against those attributes, and then manage the teams to maximize the attributes. In baseball, this might be something like how often a player gets on base, including how often he gets hit by a pitch or gets walked. In software analytics, we want to do something similar, I would argue. We want to identify the key attributes for delivering our software, measure our delivery against those attributes, and then manage our software teams to maximize them. Some of these attributes might include things like the mean time to repair a bug, the amount of cycle time between getting a feature idea into the requirement stage to eventually delivering it to a stakeholder, and then finally, the amount of technical debt in our software. I'll pause here to note that we don't want to necessarily manage software developers the way we would manage baseball players. They're certainly not paid anything close to the same. So we don't want to look at individual performance here, but rather just how our software delivery as a whole is working. I think software development is too creative and too ephemeral a process to really ascribe to individual measurement of individual developers. So in this talk, I want to talk about technical debt in practice. First of all, deciding what it is and why it matters, and then looking at some strategies for identifying it, for managing it, and ultimately avoiding the inadvertent technical debt we might incur. The definition that I'm going to use comes from Steve McConnell. He writes that technical debt is happening when we take a design or construction approach in our software that's expedient in the short term, hence a shortcut, but creates some technical context that increases the complexity and costs in the long term. So it's a shortcut that's effective in that short-term period, but ultimately creates problems for us in the longer time horizon. The original definition of technical debt came from some writing that Ward Cunningham did. Ward Cunningham was one of the originators of wikis and also of the agile software development movement. And he writes that shipping first-time code is like going into debt, that a little bit of debt is okay as long as you pay it back promptly. And the emphasis here is really agile software development, where we don't really understand all the requirements the software might have. And we have to wait until we put it into production to really understand what we should have done in the first place. And so the emphasis that Ward Cunningham has is to make sure you go back and fix those things once you realize what you should have done in the first place. Another approach to this is to look at the Martin Fowler quadrant. Fowler divides technical debt into different aspects of how we go about incurring it. In the inadvertent bottom row here, we don't really realize that we're incurring technical debt. So if we are prudent about it, but inadvertent. We realized, oh, we incurred technical debt here because we didn't know at the time, it was an unknown unknown. We didn't know at the time what we should have been doing. The top left quadrant, reckless and deliberate technical debt, is what happens when we do cowboy coding. For example, we go ahead and just start writing code without any thought to the ultimate design of the software. The top right quadrant, the prudent and deliberate quadrant, is one where we should probably find ourselves, where we are taking some risks with the code that we're writing, but that ultimately we know we have to go back and do something about that. And that's not a bad place to be necessarily. The final sort of conceptualization of technical debt that I really like is one from Felix Krueger at the University of British Columbia, who writes about how we can think of the different things that we should work on as software developers as being divided to four different areas. The green stuff is the visible features that stakeholders like. Those are the things that you can point to and say, look, we did this in this particular iteration. And the yellow things, the hidden architectural features, still have positive value, but they aren't necessarily visible to end users. Finally, we have bugs and defects. That's the red quadrant there. And technical debt is similarly something that has negative value for our software, but is often invisible to the stakeholders. So this is another good way of thinking about what technical debt is. In a book that I worked on with some colleagues, we looked at a bunch of different other causes for technical debt. And what we found was that there's actually quite a few different areas where we could properly describe it as technical debt. Conventionally, we think of technical debt as being about the design or about the code, but we thought that there was also some technical debt or opportunities for incurring technical debt in places like shortcutting the requirements process, shortcuts in the deployment process, and then also, and importantly, some shortcuts in how we actually organize our teams and manage the sort of social interpersonal dynamics of our software development team. So it's a holistic view that looks a bit beyond just technical debt is all the bugs that exist in my code. Why does technical debt matter? Why is it important? To explain a bit more about this, I want to look at technical debt in big science. I've worked on a couple of different projects on research computing and research software, one with the Square Kilometre Array, and another one with the Large Hadron Collider's High Luminosity project. If we look at a radio telescope like the ALMA Atacama Large Millimeter Array Telescope, which is in Chile and currently under sort of normal scientific operation, they typically have 4 phases. So there's some kind of design phase where, a lot of it is, figuring out what this thing should actually look like in order to achieve the science objectives. There's a construction phase where trucks are moving dirt around in the desert, a commissioning phase where we're trying to put all of the different pieces together and integrate them into a single whole where we can deliver science products. And then finally, the normal sort of sustainment phase where we're doing science operations. And we make upgrades, but the basics of the telescope, the basics of the instrument are already there. Like in many of these projects, the budget's quite high. So, over $1 billion for some of them. There's multiple different stakeholders. So the $1 billion often comes from different government consortia. So you have to negotiate between governments in the EU, governments in Asia, governments in North America to try and get all of them to work together, which is a hard task at the best of times. These large scientific instruments are expected to operate for decades because if the taxpayers put all this money in, they probably want to see some return for a prolonged period of time. The ultimate implication here is that the design choices that are made in that beginning phase often constrain the implementation that we see today. So for example, in the Square Kilometre Array, they made a choice to go with something called Tango middleware for moving messages around the system at a fairly low level. That's going to constrain how the implementation happens, which is still underway and probably won't be finally at its operational phase for a few years yet. Another part to think about is the social debt that's incurred, right? Because these organizations are made up of multiple consortia, then each of these consortia has to do its own thing and as well integrate with all the other consortia. So for example, in the Square Kilometre Array, there's a group of people involved in working on the fundamental signal processing for getting the sort of raw signal into some kind of scientific product. There's people who are involved in putting together the hardware and figuring out how to lay cables and so on. And then there's folks, some of whom might be in the audience today, who are working on things like receiving that science product and delivering it to the scientists around Canada and the United States and other parts of the world. The note here that the design is sort of in a vacuum. It's definitely not agile, right? We're not able to release software and see how that software works at this point. Nothing's happened. There's no shovels in the ground. There's nothing tangible that we can implement software with. But that doesn't mean that we don't know what we're doing. In fact, a lot of these projects have people who already have done something similar. So if you worked on the ALMA telescope, people from that I know have been consulting on the Square Kilometer Array. It's a pretty small community after all. And these people have a lot of experience and are very, very skillful software developers. So as a result, the design isn't really just someone making stuff up. They have a pretty good idea of what needs to happen. Prototypes and pilot studies are happening to try and figure out if that's the right way to do it. The commissioning phase is an interesting one. And in the ALMA case, if you read some of the papers that were written, you can see that at this point, lots of money has been spent, lots of things have been built, but no science has been done yet. And as a result, in the commissioning phase for this telescope, and I'm sure for lots of scientific projects, there's a real urgency to get some data that people can look at, right? To make some discoveries. After all, that's what the money was for. As a result, you have a lot of time pressure, similar in my view to how you might develop a software game, where there's a real emphasis to say, let's get this thing working and delivering something. As a result, that time pressure, that time crunch often leads to shortcuts being taken. As a result, in the operational phase, you often have people trying to maintain this telescope with less funding because it's been built already, having to deal with the decisions that were made at the design phase, and also the decisions that were made in the operational phase, or in the commissioning phase, I should say, right? So the shortcuts and that lack of insight into how this thing actually gets put together. When I talked to some folks in the sort of the Large Hadron Colliders project, they mentioned that a lot of the software that currently runs in the LHC is stuff that was designed 15 to 20 years ago. And as you know, in the tech industry, that might as well be 100 years ago, right? In terms of what's changed in hardware and software since then. So there are a lot of software sustainability challenges, right? Just upgrading libraries is difficult. In the Square Kilometer Array, talking to the chief software architect there, they understand that at this design phase, they have a lot of potential technical debt and really have a way of designing a system to make sure that they understand what the technical debt is and to try and use some kind of budgeting process to keep that technical debt in some kind of scoping. A project by a colleague of mine, Steve Easterbrook, looked at the climate modeling software at the Met Office in the UK. What I want to draw your attention to here is here's all the ways in which people can, requirements essentially are generated for this particular climate model. And the one at the very top is the one I think is most pertinent to technical debt, right? Which is code cleanup, essentially refactoring the code to make it better. Often with a lot of these projects, and we see this, for example, with the climate research unit email hacks, you can see that students come along, maybe they're there for a year or so as a postdoc. They're responsible for adding some new module to the software, but they may not be trained software engineers. They may not know exactly how to, what the standards are. As a result, there's a lot of technical debt in the software that could be refactored. And so this code cleanup bubble here is emphasizing that this is something that the folks at the Met Office are responsible for doing. And I think that's pretty common to all of the projects that scientific software is used with. Now, notice that the other bubbles, I think somewhat accidentally, Steve has shown all the other bubbles as bigger, right? Because usually for scientists, the more interesting requirements are things like the physics research and the analysis and all this, right? That's the stuff that's most exciting. That's what gets you a dissertation after all. Conway's law is I think, important aspect here. I mentioned it a bit in the Square Kilometer Array sense, which is the organizational structure that you create in your project is often reflected in the sort of technical architecture design that you have in your software project. So for example, in the Square Kilometer Array, here's the setup they have, for data processing, signal processing, and so on. And so there's software modules that are associated with each of these elements, right? And then there's this regional center initiative to say, look, we're going to need someone to actually take the science products and distribute them to scientists, manage time and all that. And so each of these things ends up becoming a separate software module. And the challenge, and one of the things that we were helping with in the consulting phase, was to try and make sure that integration of these pieces was going to be effective, right? There's a lot of technical debt that can be introduced if you haven't been doing useful integration testing and designing to make sure that all of these pieces work well together. So what should we do here? I'm going to argue that we can break it into three different aspects: identify, manage, and avoid technical debt. In the context here for research software development is as you well know, I'm explaining things you already understand. You have many stakeholders, right? The faculty and researchers involved in the project, students coming along, the local administration, national research councils, CIHR, whatever, right? All of those people have something that they're interested in. There's many constraints, often very low budgets, a lot of staff turnover, there's pressure to publish. As Owen Woods, I think, explained yesterday, there's some urgency in figuring out if this is security, if it complies with security requirements. I know from the Square Kilometer Array, one of the things that they were concerned with was because they're essentially building the world's largest supercomputer, there's a lot of people interested in mining Bitcoin on this thing. And so they have to think about these security aspects and security risks in many jurisdictions, of course. There's legacy systems, right? Someone has to maintain this code at some point, often not for a whole lot of reward. And of course, lack of resources and time to do all of the above. So let's look at how we can identify technical debt. There's a couple of different pieces I want to touch on here. The first one is to think about the sort of self-admitted technical debt. And I think this really ties in nicely to the aspect of what happens when a postdoc or PhD student starts adding new elements to the software. There's a real risk that that person is not onboarded properly, that they don't understand, coding conventions, that maybe they haven't been trained in software development. As a result, self-admitted technical debt is this term that captures what you do when you say, I don't think this is the right way to implement this piece of code. So for example, here's some examples I circled in red, this is faintly ridiculous, or this is hacky. Things like that are flags for researchers to say, this is probably something that needs to come back and be looked at. And how you do that is somewhat project dependent, but for example, you might run a tool that looks for these kinds of comments and flags them for the issue tracker to say, okay, we need to come back and revisit this particular piece of code. So that's one way in which you can start trying to identify technical debt in your code base. Chances are that if you talk to people who are working on it, they have a pretty good intuition of what they don't like about the code, right? And often it's a matter of, well, we just don't have the schedule time to go and fix this. I know it's hacky, but I keep needing to postpone working on that to do some other feature development. So often just talking to developers and saying, well, what do you not like about this code base is a good way to figure out what where the technical debt is. There's some really good tools right now for doing technical debt analysis: SonarQube, CodeScene, CodeSonar, Code Inspector. Lots of different services that will help you analyze your code base and give you some metrics on it, right? This comes back to this, sort of Moneyball data science aspect I was talking about. These tools are really very useful and they work very, very efficiently. They're not very hard to install. What I would say though is that what I often see is people generate, if you run this tool on your code base with no configuration, it'll generate 1,000 errors. And it'll say you have all these problems in your code, all this technical debt. Reality is that you probably don't care about 90% of the stuff it flags. As a result, you need to configure the tool to respect the rules that you really, really want to know about, right? What is the thing that if a student commits code to your code base, you really want it to be flagged if this rule is violated? For example, it's a method that's longer than 50 lines or something. Once you've configured the tool, it can be very, very helpful. But what I would say is, more importantly, is to track the change over time. So if the line is, you have, I don't know, let's say it says you have $700,000 of technical debt. Well, that is what it is. Who knows what that means? But if it suddenly starts to jump after a new student or a new person comes onto the project, that suggests that maybe something is not quite right here. So tracking the change over time and tracking the delta between different projects is usually a good use of resources. As I mentioned, I think you should probably aim for something between 7 to 15% of your backlog to be technical debt. I think it's a good thing because it reflects that you don't know all of the requirements for your system, and as a result, you're taking some risks. You can't really, make good advances in software if you're just, doing what's expected of you. So some technical debt reflects the fact that you are trying things that may or may not work out in the long run. Finally, I would say that when you go about identifying technical debt, you need to cast a pretty broad net. You need to be able to look at things like tests, your infrastructure as code scripts, as well as this social debt that I mentioned, right? If you have different units that are involved, for example, maybe there's a team in Japan that's maintaining a piece of the software. That suggests that there's potential technical debt when it comes to integrating the different modules together. Finally, when it comes to identifying technical debt, I think one of the things that I've found most useful in the last 5-10 years is this idea of sort of lean software development. Here, I've taken a screenshot from Mick Kirsten's book, Process to Product, Project to Product, I think, that looks at how we can implement sort of a lean idea of software development, this flow model of, new features come in, and at the end, we get some kind of released feature to the customer, to the stakeholder, however you want to think about it. Doesn't matter in particular, what the specifics of the lean framework are, but thinking about the different things that flow through the software development pipeline can be really useful. In Mick Kirsten's approach, he divides this into 4 different sort of categories of, similar to what Felix Krueger's ideas were, right? We have features, we have defects, we have architectural, risks like security problems, and then finally some technical debt that needs to be repaid. And what he's arguing is you should first of all identify those things and then assign some level of attention or some resources to dealing with those throughout the life cycle. Okay, so if we have some idea for what technical debt might exist in our system, we've run a tool, for example, and we found that it reports all these problems. This file has a lot of large methods and so on. Now, what do we do with that information? How do we manage that technical debt? I think there's a couple of different approaches, and it really here it's the sort of famous software phrase, which is it depends on the context of your organization, your group. But I think there's a couple of sort of high-level ideas that you can implement. The first would be to think about things as technical debt items. So like I said earlier, capturing technical debt in some kind of issue tracker is really important. Once you've got it identified and named, now you can actually manage it somehow, right? You can see it sits there in your issue tracker, and you need to assign resources or money or time to fixing it or doing something with it. So having an issue tracker tag or a label, like if you use GitHub for software development, it comes with predefined issue labels like bugs. You can add one there for technical debt that just reflects that these are things we need to come back to at some point. A risk register is something similar. When you make design decisions, and hopefully you're capturing these somehow in your documentation, what you can capture there is how risky is the design that we've chosen, right? What is the chance that this particular design approach is going to be, subpar for the solution that we're hoping for? So in the risk register, you can capture the fact that the risks to this design choice are really these things here, and we need to come back and revisit that, right? Did this design actually end up working out for us, right? When we chose Tango as the middleware, and we did all these pilot studies, there's still a risk that ends up not scaling or it ends up not being performant enough. And we should come back and revisit that choice later. Finally, like I was mentioning, you should manage the metrics that you've defined. Again, the metrics are going to be somewhat, specific to the project you're working on. For example, I would assume that you would have some kind of quality indicators such as latency or availability and whatever is important to you, or maybe the science goal, how long does it take to actually run the model? There's some metrics that are somewhat, generic across software projects. So for example, mean time to repair a bug, the cycle time between someone having an idea and then that implementation, being released in the software, the risk exposure. So managing those metrics and figuring out what the trends are. And then finally, the sort of tough conversation here, to have that talk with whoever's responsible for the budget and calling that out in the budget. Now, I think that, it's been great to see research software engineering getting its due to some extent, right? To having societies that recognize research software engineering, to have conferences like this, where people can sort of recognize that there are other people doing the same job. But I'm not sure we're yet at the place where in our NSF proposals or in our NSERC proposals, we can say, hey, I'm going to need some money to allocate to technical debt reduction, right? We've got a few projects from Canary, for example, that try to fund, hey, we're going to try and make the software more maintainable, more usable by the general public, for example. But I think we need to still do a lot more work to make sure that people realize that some of the key foundational insights that are generated from astronomy, from physics, from whatever, really rely on software that, if we don't keep maintaining it, is not going to work very well, and it's not going to be able to do that science for us. So having that budget conversation, either with the PI or with the funders, I think is an important aspect of managing technical debt. We can think about this again from the backlog perspective. So if we think about the visible features as well as the technical debt, the defects in the architecture that we need to work on, we can look at the backlog. So traditionally, maybe our backlog looks something like this. We just have bugs to fix and features to implement. That's, I think, the view most people have of software engineering or software development. Whereas in reality, we want to shift to this model that says, look, we've got, yes, bugs to fix and features to implement, but we also should think about the architectural work that we need to do to prepare for, let's say, release 2.0, and the technical debt reduction we need to do, right? We took shortcuts to get from A to B. Now we need to go back and make sure that we're not going to, accrue a lot of interest because of those shortcuts. One useful thing to think about is sort of the iterative patterns you're going to take. There's a couple of anti-patterns here, the ones in red. So the first one in the top left is you aren't going to need it, YAGNI, which is we don't have any technical debt, we don't have any architecture work to do, we're just going to go blaze ahead and work on feature development. That's sort of the third-year software engineering student approach, right? We're just going to hack everything together for the deadline and then throw it over the wall, and someone else will worry about it. So obviously not something I recommend. The other anti-pattern is D, the rework anti-pattern, which is similar, but now we're going to go back and fix all of the things that we realized we screwed up in the first place, right? So we start with a bunch of feature development, and then as time goes by, we realize we're not as able to release new features, and we're going to have to increase the amount of architectural work, of rework we have to do to bring the software back to where we started. The alternatives that I think do work, and I've seen in practice, are the top right, which is the sort of idea of a hardening sprint or hardening iteration. So here we would work on, for example, we have a deadline of getting things out the door by November 1st. We work on sprints up to November 1st. So those first 3 green arrows. And then if things get released, we come back and we do a hardening sprint where we go back and fix all of the problems, all the technical debt we incurred in those first 3 iterations. The challenge here is it really requires organizational discipline to commit, a week, 2 weeks, whatever it is, to go back and fix things. So that's a week or 2 weeks where you're not working on new features. You're just working on fixing technical debt and improving the architecture. Iteration 0 is the idea that before we even start working on features, we're going to have an iteration where we just start thinking about what the design of the system should look like. So that's the one in the middle. We start with architecture, then we scale that down and then build up the feature development. And then finally, the scaled architecture framework, scaled agile framework says, what we can do is just think about working on architecture and technical debt reduction side by side. So as we go along, we're working on features, yes, but some people, part of the time, or a dedicated team, however you want to set it up, are going to work on technical debt reduction and working on the next sort of architecture runway that we have to think about for the new version of the software, right? And so this is the approach that the square kilometer array software folks are taking. And it works well if you have enough of a sort of resource budget to allocate people to doing the architecture work alongside. Okay, if we've talked about identifying it and managing it, the last thing that we can think about is, well, how do we just try to build software deliberately enough so that we're not going to incur this inadvertent technical debt? So as I said, I think some technical debt is unavoidable, and you should aim to have some. But you should be prudent about it, right? According to that Fowler quadrant, you should be doing it deliberately with the knowledge that, yes, this is bringing technical debt. So how can we do future proofing on our systems, especially if some of you are involved in large scale software projects like Square Kilometer Array, where you're designing things for 10, 15 years from now. So there's a couple of different ones that we can look at. And if you have other questions about this, I'm more than happy to answer them in the Q&A. We can try to modularize the system so that it can be evolved pretty quickly and easily. So for example, we might say we're going to make each of the elements of the software, the Square Kilometer Array, into its own module, and each module is very independent from the other, some kind of sort of microservice version of the architecture. And the challenge here is, the trade-off here is that we have integration risk. Integration risk meaning there's things that we're going to do in each of these modules that makes it harder to make them work together. For example, performance often suffers if we have too many modules in our software. We can modularize it for release so that we know, okay, this piece is going to come out, in 2021, then this piece will come out in 2022. The trade-off there is that, you might end up with duplication of some of the services that are common to all of those different modules. We could try to defer our design decisions until the last responsible moment. I think this is a good practice anyway. The key here is, what is the last responsible moment? Rebecca Werfsbrock has worked a lot on this, and I encourage you to read some of her work. Again, I can answer more questions about that. But the idea is that you don't want to make any decision until it's irresponsible to not make the decision. And I'm sure we've all worked on projects where people have not made those decisions even past the last responsible moment. The idea being that, for example, if we come back to middleware for messaging in these different modules, maybe there's 2 or 3 different competing standards that we could choose from. The last responsible moment idea would say, well, we don't need to choose one until this particular milestone happens in the project. And so there's no point in worrying about that. Let's keep thinking about all 3 of them as options until it's no longer feasible to keep going with all 3 of them. So the trade-off there is the schedule might be slowed down. You might end up duplicating work because someone has to build, for each of these different middleware packages. Instead of knowing, yes, we're taking package number 1, go ahead and build your API or whatever for that particular one. And then finally, I think the one that I have most experience with, and the one that we applied at the Square Kilometer Array project, is to evaluate the design and the architecture regularly with some kind of scenario approach, to test it regularly with scenarios. And the trade-off there is that it's costly to do these analyses, and it's a different process than people are used to. Let me explain this in a bit more detail. So the idea here is that we're going to think about 3 different elements of our system. The first is the mission goals. In this context, it's usually the mission goals. Those are often the scientific objectives that people have. So for example, I really want to see just after the Big Bang as a radio astronomer. That's a mission goal that the Square Kilometer Array has. In my experience, so that's pretty high level. In my experience, it's pretty rare to have more insight into the mission goals than that. People have this tacit understanding of why they're building the software, but they don't necessarily have a detailed understanding of what that means in terms of the software itself. So and this is from the Software Engineering Institute's package of technologies, of approaches. The quality attribute workshop is a way to really dig into what is it that we think are important qualities of this system, right? What is it that we really need to do? So for example, we ran a quality attribute workshop with the Square Kilometer Array folks to really try to dig into what everyone in the room, all the different stakeholders, the scientists, the software developers, the sort of business-facing folks, the funders, really wanted the telescope to be able to do, and what the software had to do. And so that generated scenarios, things where we could say, look, in the context of discovering a new pulsar, the software has to be able to rapidly, schedule that sort of pulsar observation time and figure out how to move everybody else around so that the scientists still get their allocated time and so on. So there's a scenario where the telescope software has to respond to that scenario. Once you have an idea for what the mission goal is and what, how you can operationalize that, how when you're meeting that goal, you can start to design the system accordingly. And attribute-driven design at the top right there is a technique for trying to say, okay, well, here's the key quality attribute, it's latency or something. This is what we're going to have to do to meet that objective. Now note here that this is not something that outside experts come in and tell you how to do it, right? The people who are designing the Square Kilometer Array software know all of the details here. They ask for help for specific technical issues, but they understand how to do the design. It's mostly just a matter of facilitating an understanding of, well, what are the things that you really needed to do, and how do you prioritize those things? So as a way of avoiding technical debt, this is a way of thinking about, a little bit of upfront design, right? Not that sort of you aren't going to need it approach that I showed earlier. Thinking a bit about what is the design going to look like for this large project that's dealing with unprecedented levels of or volumes of data, unprecedented, scientific challenges and technical challenges with moving bits around and processing all the data in time. And coming back to that point I mentioned earlier, which is this isn't just a sort of, let's do the design once and then, then we'll just charge ahead and see how it works. The ideal would be that you come back each time and see, okay, we've refined the design, and now here's a new, this new design should be tested against those scenarios that we came up with. Okay, if we have a scenario that says, latency is really, really important here because we're dealing with so much data, does the new design still help us with the latency problem to the best of our knowledge? And so you can use this as a way of testing the architectural design approach you've taken for this particular system. And we've used this successfully in the square kilometer array. So the usual way these projects work is you have a preliminary design review and critical design review of each of these modules with outside experts sort of assessing whether you're ready to go ahead. And this approach was very successful in helping the software sort of components of square kilometer array pass their critical and preliminary design reviews. And I think it worked really, really well. So for technical debt in research software more generally, outside of these large projects, I think it's very rare to see peer review of research code, unfortunately. So we do peer review of our science and our methods and all this all the time. Very rarely do we look at the code that we use to generate those insights. And I think that that's a real risk. For example, there was this famous error in Excel. Maybe you shouldn't be using Excel is the lesson there. I don't know, but everybody uses Excel, so we should probably just deal with it. And certainly in my experience doing my research, there's been times when someone has made an assumption or used a file that was the wrong file or whatever. And peer review is really important. Peer being the other people in our lab, maybe, to catch those problems. And at big data volumes, which is what we're dealing with now, that's even more likely. Right? In the volumes of data that the square kilometer array deals with, bit errors could be very, very dangerous for the long-term archives of the research data that they're storing. I think the ways to avoid inadvertent technical debt are things like this conference, talking to other people who have similar problems, the Society for Research Software Engineering in England, or in the UK, I should say, initiatives like software carpentry to try and upskill the scientists who are being trained today, archival repositories to share data and code with other folks, papers with code is a good example here for machine learning, and then finally reproducibility efforts. If we emphasize that, hey, we need to be able to look at the code that inspired these results, that will make all of our scientific contributions that much stronger. So to avoid technical debt, I think, like I said, we want to think about technical debt as something that's useful for us to learn more about the domain. But the technical debt that we've incurred somewhat recklessly or inadvertently is stuff that we need to go back and try to fix, right? Once we've learned what we need to know about the domain, we need to go back and fix the technical debt that exists in the software that we're writing. So to sum up, I think that software is entering this sort of Moneyball era, or has entered this Moneyball big data science era. And software analytics are a good approach to try and identify what those key metrics are, to measure how well we're doing on those metrics, to manage our teams, to try and maximize those metrics, and then finally to figure out how to avoid technical debt in the first place. And the good news is that it's never been easier to do this. There's great tools out there for doing it. We have a really good understanding of how technical debt is incurred. There's lots of research in this. And so I encourage you to ask questions in the Q&A if you would like to, or reach out to me in person to discuss it some more. Thanks very much for your attention.